All right, let's get you sorted for your GCSE chemistry exams with this explainer on the reactivity of metals. If you're doing the AQA spec, this is section 4.4.1, and trust me, we're going to cover everything you need to know to feel totally confident on this topic.
So, here's our plan. We're going to start with the absolute basics. What even is metal reactivity? Then we'll get into the reactivity series itself. After that, we'll see how it's used in the real world with displacement and getting metals out of the ground. We'll tie all that into oxidation and reduction, and for you lot aiming for those top grades, we'll finish with the higher tier story about what the electrons are really up to.
First things first, what does it really mean when we say a metal is reactive? Well, it all comes down to two key processes that are happening all the time in chemistry. They're called oxidation and reduction. Let's get our heads around those before we go any further.
Okay, so here's the deal at its simplest level. Oxidation is when something gains oxygen, and reduction, that's when something loses oxygen. Simple as that. The key thing to remember is that they're basically a package deal. They always happen together in what we call a redox reaction. It's kind of like a chemical tag team.
Right, now that we've got that idea, let's move on to the star of the show, the reactivity series. Honestly, the best way to think about this is like a league table for metals, like in football. It ranks all the metals from the most reactive superstars at the top down to the ones that, don't really do much at all at the bottom.
But what are we actually measuring here? What puts a metal at the top of the table? It's all about how keen a metal atom is to lose its outer electrons and turn into a positive ion. The easier it finds it to do that, the more reactive it is, and the higher up our league table it goes.
And here it is. This is the list you've got to get familiar with. At the very top, you've got the big players like potassium, super reactive. As you go down, they get less and less keen to react, all the way down to copper. But hang on, you'll spot a couple of non-metals in there, right? Carbon and hydrogen? They're not there by accident. They're super important benchmarks, and we'll see why carbon is such a game changer in a minute.
So, we've got our league table. What can we actually do with it? Well, this is where it gets really powerful, because we can use it to predict what's going to happen in certain reactions, especially something called a displacement reaction.
The golden rule is this, and it's beautifully simple. A more reactive metal will always kick out or displace a less reactive metal from its compound. Think of it like a chemical wrestling match. The stronger, more reactive metal always wins and takes the other's place.
And you can use these 4 simple steps to get it right every single time. First, spot the single metal and the metal that's already in a compound. Second, find them both on the reactivity series. Third, if the single metal is higher up the list, it wins. Displacement happens. And fourth, if it's lower down, nothing. Absolutely nothing happens. Easy, right? Okay, quiz time. Let's put this into practice. Imagine we drop a piece of iron into a beaker of blue copper sulfate solution. What's going to happen? Have a look at the series. Where's iron? Where's copper? Who's higher up? What do you think?
Yep, you got it. Iron is higher up the series than copper, which means it's more reactive. So it literally just pushes the copper out of the way, takes its spot in the sulfate compound, and you're left with iron sulfate and solid, pure copper.
Now, this isn't just for cool experiments in the lab. This is how we get tons and tons of metal in industry. Remember that carbon we snuck into the series? This is its moment to shine. Any metal that sits below carbon in the series can be pulled out of its ore just by heating it up with carbon. Because carbon's more reactive, it just displaces the metal, setting it free. It's how we get iron for steel.
Okay, let's pull all these ideas together now. We're going to loop right back to where we started, with oxidation and reduction, and see how they perfectly describe what's going on in these displacement reactions.
Let's take a look. If iron reacts with copper oxide, the iron gains the oxygen, right? It becomes iron oxide. So the iron has been oxidized. And the copper oxide? Well, it loses its oxygen to become pure copper, so we say it has been reduced. See how it works? The more reactive metal always gets oxidized, and the less reactive metal's compound gets reduced. Every time.
Right, for everyone doing the higher tier paper, we need to go one level deeper. Talking about gaining or losing oxygen is great, but the real universal definition of oxidation and reduction is actually all about electrons. And the best way to remember this, and you've probably heard it before, is OLIRG. It's a lifesaver. OLIRG stands for oxidation is loss of electrons. Reduction is gain of electrons. Just burn OLIRG into your brain and you'll have redox sorted forever.
So let's look at our iron and copper example again, but this time think about electrons. The iron atom starts off neutral. It then loses 2 electrons to become a positive iron ion. Oxidation is loss. So the iron atom has been oxidized. And those 2 electrons, they get snapped up by the positive copper ion that's floating in the solution. Reduction is gain. So the copper ion is reduced and it becomes a neutral copper atom. That's what's really going on.
Okay, to wrap this all up, here's the challenge for you. Rusting, as we know, is just the oxidation of iron. So have a look at the reactivity series again. How could you use a more reactive metal to stop an iron bridge from rusting? This is a real-world technique called sacrificial protection, and based on everything we've just covered, you have all the tools you need to figure out exactly how it works.